Avoid contact with ill individuals and insist they isolate themselves until they have recovered and are symptom-free. Clean and sanitize frequently touched common surfaces and high-traffic areas in your home and workplace several times a day. Share these guidelines with others and help prevent the spread of illness and maintain a healthy environment. An ounce of prevention is worth a ton of cure.
Chapter 1 starts off with chemicals, what they are and where they come from. Now, people, right at the bottom of the page, you don't have to worry about that first part. Chemistry is simply the study of matter, okay, what the substance is made of, and why it behaves in the way it specifically does during a chemical reaction. All right. Now, in chemistry, we try and find patterns so that we can use these patterns to predict how things will react. For example, you all know that when an acid and a base react, the product is a salt and water. That could be considered to be a pattern, which we can use to predict what different acids would react to form. No. All right. So, they say we can ask useful questions like, how can we obtain useful materials from the earth? And how can we make new substances? Now, people, for example, the plastics industry is a rapidly growing industry. They design new materials every single day. Some are useful, some are not. All right. Although plastic was thought to be extremely useful, and it is, but nowadays there is a very, very large problem with plastic pollutants. No, plastics are persistent. They don't want to degrade. Yes? Yes, but then it releases carbon. Plants can't use carbon. They use carbon dioxide. It's one of the ways of disposing of it and trying to get it back into the cycle, but it's not a perfect method. Okay. If it decomposes under bacterial decomposition, then it usually ends up as carbon dioxide or methane, which can be burned to form carbon dioxide and water vapor, which can be used by the plants again. All right. So there are problems with that, but that's environmental chemistry. All right. Now, the next section there in your textbooks, page 3, solids, liquids, and gases. In other words, the kinetic theory. What does the kinetic theory tell me? Yes, particles. Matter consists of particles. These particles have energy so they can move. There are spaces. And there are forces between particles. 2 types of forces, attractive and repulsive forces. Okay, now solids. Solids consist of particles. What do we know about the movement of the particles in solids? Yes, they vibrate around a fixed position. In other words, in solids we say particles are orderly arranged in a crystal lattice. The movement is a vibration about a fixed position. What do we know about spaces in solids? They are very small, all right. The attractive forces are quite strong because it holds it rigidly in position. The repulsive forces we know, whether it's a solid, liquid, or a gas, when we start forcing particles together, then the repulsive forces come into action. But if we don't force them together, we can just ignore the repulsive forces because there are no repulsive forces in this pen. All right, until I start smashing the particles together, then the repulsive forces come into action. All right, so that would be the kinetic theory with respect to solids. In terms of liquids, matter consists of particles. How can I prove that in terms of liquid? If I poured some water out on the floor, tomorrow morning I'll come back. Will there be any water left? No, it will have evaporated. Okay, so the tiny particles have escaped from the liquid and it formed the gas, so it's disappeared. All right. Also, I can make, on a cold morning, I can make water vapor condense into droplets. Okay. So, in a gas, we have particles. The particles can move. What do we know about the movement in gases? We call the movement diffusion. So the movement of liquid and gas particles, we refer to it as diffusion. Technically, solid particles can also diffuse, but it is so slow and so little over such a long period of time that we ignore it. Okay, we just completely ignore it. So diffusion, if I'm referring to particles moved by diffusion, I'm talking about a liquid or a gas. Okay. So they move, they can move freely. Definition of diffusion is spontaneous movement of particles. Okay, so what do we know about the spaces in a liquid? Can I compress a liquid? No. Can't compress a liquid. Can I pour water in a bottle and compress it? No. Yes. Okay, so the spaces are fairly small. We say bigger than in a solid, but smaller than in a gas. Attractive forces in liquids are slightly weaker than in solids, because in the liquid state, it has partially overcome the attractive forces holding them in a fixed position. Yeah. I don't know. Pity. Okay. Yes, but under normal conditions, it's very, very, very slightly compressible, so little that we ignore it. But I don't know about hydroforming. Okay. People, then, once again, the repulsive forces play a role when we start forcing them together. Okay. When we look at a gas, gases consist of particles. I know that because if I have a smelly gas on this side of the room, within a few moments on the other side of the room, you can also smell it. How did it happen? Well, the particles would have had to move. So the particles went into your nose, dissolved there in the moisture on the nerve endings, okay, and we can smell the smell. So gases consist of particles. These particles move by means of diffusion, and I'll have a look at diffusion just after this. There are spaces between gas particles. What do we know about the spaces between gas particles? Small or big? Very large, because gases just tend to spread. So if I have a bicycle pump and I pulled some air into the pump and I closed the front, I could squash the gas. All right. So we say gases have fairly large spaces. The attractive forces in gases have been overcome completely. So the attractive forces are so weak, we say there aren't any. Nothing holds the gas particles together. Because if I open up a cylinder of gas, it spreads. And if I open up the classroom, it will spread further. Okay. So the attractive forces in gases are very weak, so weak that we say they are non-existent. And then repulsive forces, once again, when I start forcing particles together. Okay. In your textbooks, there they have a look, page 4 and page 5, at the kinetic theory for solids, liquids, and gases. Then they have a heading there, Brownian movement. Okay, what is Brownian movement? All right, Brownian movement, die rympie, zigzag, erratic movement of solid particles suspended in a liquid or gas. So we have two phases. We have a solid in a liquid, or we have a solid in a gas. The easiest illustration of Brownian movement, if you sit inside a room where the curtains drawn, a shaft of light shines between where the two curtains come together, you can see the little dust particles just moving aimlessly, dancing about in the air. That is Brownian movement. The dust particle is the solid particle, and the air, we can't see that. The solid particles bump into the air particles, and they move erratically. All right. The difference between Brownian movement and diffusion, in Brownian movement we have a solid particle suspended in either a liquid or a gas. But in diffusion, it is the particles of the liquid or gas that moves. In other words, if there wasn't diffusion of gases, would we be able to observe Brownian movement? No, because the air particles diffuse, they are moving. And they bump into the solid particles that are very light. Okay, we get the Brownian movement. Do you understand that? Okay, even though this classroom is closed up, because we have air in it, there is diffusion. Some of the textbooks keep on saying that diffusion occurs from a point of high concentration to a point of low. Yes, it does. But if the concentration is spread uniformly throughout, it still keeps going. It doesn't stop. Do you understand? All right, that is quite important because that's a misconception that they sort of tend to confuse everybody with. All right, so in your textbooks there on page 5, we have Brownian movement. Now, still there on page 5, in terms of diffusion, one very well-known experiment, we take a horizontal tube. On the one end of the tube, we put in HCl, and on the other end, maybe I should have done it the other way around. Maybe I should have done some acid, HCl, and over here we have NH3. Okay. They put 2 cotton wools soaked with each of the solutions simultaneously into this tube. Now what happens is when hydrochloric acid and ammonia meet, it forms ammonium chloride. And this stuff is white, smoky. It looks like smoke. All right. It's actually tiny solid particles that are formed. Okay, ammonium chloride. Now, if diffusion of the different gases occurred at the same rate, we would expect them to meet somewhere in the middle. But this doesn't happen. Where does it meet?
Doesn't it meet nearer to the
It forms the ammonium chloride ring closer to the hydrochloric acid than to the ammonia. What is the explanation of it? Smaller, lighter particles can move faster than bigger, heavier particles. Do you understand that? All right. So, in terms of diffusion, not all gases diffuse at the same rate. We tend to find that the lighter gases diffuse faster than the heavier ones. That's the first factor. The second factor, if I went and investigated diffusion in gases in relation to diffusion in liquids, we are going to find that diffusion in gases occur quite rapidly, while diffusion in liquids takes slightly longer. All right. If I take a smelly perfume and I release it on one corner of my class, within moments you can smell it in the next corner. But if I took a container and I dropped a single drop of blue ink into it, it takes a couple of seconds for this ink to slowly disappear as it spreads into the water. Do you understand? So, The second factor then that influences the rate of diffusion is the phase. Gases diffuse faster than liquids. Why? In gases, what do we know about the attractive forces? Almost non-existent. They've been overcome. In liquids, the particles are still under the influence of the attractive forces, so they aren't completely free to just move. All right. They are held together very slightly by these forces. The third factor then that will influence diffusion is the temperature. And just very simply, temperature is a measure of the average kinetic energy of the particles. So at a higher temperature, particles have more kinetic energy. If they have more kinetic energy, they can move more. All right. So hotter temperatures, faster diffusion rates than lower temperatures. If I did the exact same experiment in a fridge or in the freezer, then it will take much longer to form this ring, although it will still form closest to the hydrochloric acid. Okay. So you met me. On a hot day, it's going to go faster than on a cold day. Yes, yes. If you warm the one, it's going to go faster than the other. Okay, so I can mess around with this experiment. I can go and warm up this. Okay. Yes, then it's going to go, it's definitely going to go faster, no? All right. So, 3 factors that influence the rate of diffusion.
3 factors that influence the rate of diffusion.
Okay, Joshua. All right. That is there in your books on page 5. Now, the next section, this chapter is so 'n bietjie los en vas. Okay. This next section, the heading is making useful substances, and it sort of goes about how do we separate things from each other. If I have a bag of sugar and some other kid has been messing around with it and mixed it up with some sand, how can I separate the sand and the sugar? I would dissolve, put everything in water. The sand's not going to dissolve. The sugar will dissolve. I can filter it. I'll be left with the sand, and then I can evaporate off the water. Okay, so a lot of these things are just common sense. If I have iron filings distributed among salt grains, how will I get the iron filings out? I will use a magnet, because one of the components is magnet. Yes. Because you don't get the filings off the magnet. Okay. So this is what this next section is about. Yeah. Okay. Sugar and salt. For example, I could use petrol. Both sugar is molecular. Okay? Because it's covalent bonds between the carbons and the hydrogens and the oxygens. And salt is ionic because it's a metal bonded onto a non-metal. We'll come to the bonding in the next section. Now, in general, there is a rule that says like dissolves like. Water is the exception because it's a polar molecule, so it tends to dissolve both. But petrol, for example, is a molecular liquid. So sugar will dissolve in petrol, but salt won't. So I could shake it up in some petrol. I can filter off the salt, and then we can wash the sugar from the petrol with water. The petrol and the water won't mix, so I shake it up. The sugar will dissolve in the water because it's more soluble in the water than in the petrol. And by doing that, you can you can wash the petrol and to remove the sugar. So it's not impossible, but you need to know certain things to do that. But that is what they do when they go and start working with these funny things. All right, so in your books there on page 6, separating mixtures, they say mixtures of solids and liquids like seawater, we can evaporate off the water, we'll be left with the salts. Mixtures of 2 or more solids, such as the ore in the extraction of metals. Now, we haven't done that chapter yet, you only do that in grade 12, but the first one of the first crude steps is to remove all the impurities from the ore. We don't want all the rocks and sand, we specifically want the ore. So there are specific ways, they use specific solvents that they know will dissolve certain things. All right, like the sugar and the petrol. Then mixtures of 2 or more liquids. How would I separate them from each other? Yeah, petrol and alcohol. They have different boiling points, so I can do a distillation of the liquids. If they don't mix, water and oil, I can decant. I can just run the one off from the other. You get a special decanter that opens on the bottom, so you run the more dense liquid out first. And you can close the tap and you're left with a less dense liquid in the container, or you can just pour it off. Okay. So that is just basically what they refer to. 2 or more gases. Well, gases can also be done by distillation. They're going to have a look at mixtures of solids and liquids. Now, when I have a mixture of a solid and a liquid, for example, I take sugar and I've got it in water. If I've got sand and water, I can filter it off because the sand is not soluble. Now, well, let's say I have pure sand with no other minerals and stuff in it. Okay? The sand won't dissolve, or the one component doesn't dissolve, then I can filter it. Okay? Yes, you can also leave it to settle. The heavier particles go down, and you can decant some of it. That would also work. If I have a substance that dissolves in the liquid, like sugar that dissolves in the water, well, if I wanted the water afterwards as well, then I would have to do a distillation because the water will boil off and I'll be left with the sugar. But if I don't need the water, I can just evaporate off the water and sugar crystals will be formed. Okay. Sometimes I have, if I want to make copper sulfate crystals, I've dissolved the copper sulfate in my solution. I will evaporate off some of the water until my solution becomes saturated. And then I will leave it to stand and it will form crystals in that solution. And then I can just pour off the liquid and I will be left with pure crystals. They talk about the process of crystallization. Okay. We use crystallization to make salt in Walvis Bay. We have these dams of seawater that have been pumped into big pools, all right, and sunlight evaporates the water. And as the water evaporates, the least soluble salt in the water crystallizes first. So then they can pump it to a next dam, and that one evaporates more water, and then the next soluble one will crystallize, and in that way we can remove the salt. Brownian Movement, and then Brownian Movement in comparison to diffusion. How do they differ? What is diffusion? Yes, Brownian Movement is a solid particle, very tiny solid particles that don't just fall down to the ground, because they are so tiny and so light they get bumped around by the air particles or the liquid particles. Yes, then you can see the little dust particles floating around. That is Brownian movement. So it's a solid particle that is suspended in either a liquid or a gas. while diffusion is just very simply a spontaneous movement of particles. If there was no diffusion, we would not see any Brownian movement. Because as a result of the random movement, for example, of the gas particles, they bump into the dust particles. We can't see the gas particles, but we can see the dust particles when light reflects off them. Okay. So, they are connected, but it's not the same thing. We get Brownian movement because of diffusion. Okay. You can compare Brownian movement to, for example, if I put a balloon into the air, and I say to you, keep it up in the air for this period. You will smack it upwards, and it will come down, and you will smack it upwards, and it's going to float. Okay, that would represent Brownian movement. You would be the gas particles, the balloon would be the solid particle. Okay. The next section then, there on page 6, refers to making useful substances. And over here it's about how to separate different things from each other. I think we just started with this. Sometimes it's easy to separate things. If I've got large enough pieces, if I must separate sand from bricks, what will I do? I'll throw it through a filter with small enough spaces for the sand to fall through and the bricks to be left behind. Or even more, on a more basic level, I can physically pick up the bricks and pack them one side, and I will be left with sand and bricks. But sometimes it's not as simple as that. If I go and have a mixture of sand, of sugar, sugar and sand. Now I can go and sit physically and pick them out. It's just going to take very, very long, but it's not impossible. But there's an easier way. I can put the sand and sugar mixture into water, because the sugar will dissolve in the water, but the sand won't. Then I can filter it off, and I'll have sugar water. I can evaporate off the water, and I'll have my sugar again. Well, pepper will float on water. It's not soluble. Salt is. So it's easy if the one part is soluble and the other part is insoluble. Because then you can dissolve it in a solvent, and the insoluble part you filter it out. And then you evaporate off the solvent. But what happens if I have sugar and salt? No. Okay. Yes. Yes. Okay, people. There's a rule. It's a very basic general rule in chemistry. And the rule simply says, like dissolves like. In other words, if I have a molecular liquid, it tends to be able to dissolve molecular solids. If I have an ionic liquid, it tends to be able to dissolve ionic substances. But we've got water in between. Now, water is molecular, but water is a very special molecular substance. Why? The molecule is polar. It's got a slight positive and a slight negative side, which means that water can sometimes dissolve ionic substances. So if I have sugar and salt, I can shake it up in water, but I'm going to get sugary, salty water. I won't be able to separate it. He says we use petrol. Why? Because petrol is molecular. It's got a low melting and boiling point. No? It evaporates fairly easy. It's molecular. So you can shake up the sugar and the salt in some petrol. Which part is going to dissolve, sugar or salt? The sugar will dissolve. Okay? Then I can filter off the salt. Now I must get the sugar out of the petrol. Now one way is to evaporate off the petrol, but in actual fact what happens is it'll contaminate the sugar. But what you can go and do is, water does not dissolve in petrol. So what they're going to do is they wash the petrol. They add water to the petrol with the sugar in it, and they shake it up. The sugar is more soluble in the water, so it's going to dissolve in the water, and they can, yes, into the water, and then they can decant the petrol from the water. You must be careful to wash out all the sugar. Because the moment the sugar gets into the system, because of the heating and the burning of the fuel, the sugar, when it burns, it forms sticky, tarry, black carbon. If you've washed it properly, yes, you can. But you would maybe have to wash it a second and a third time. You understand? Yeah, so that it is usable, but it's not impossible. Okay, it's not desirable because the organic substances, the petrols, you mustn't swallow them. Okay, they can give you a chemical pneumonia. That's one of that. That's why when kids swallow furniture oil, it's so dangerous. They can get a chemical pneumonia, and the chemical pneumonia. That's even worse because there's acid in it, yes. And there's acid in the batteries that can affect the different parts of your colon. Yeah. Mm? No, that's crazy. No, not good. I don't know. But it's not good at all. That's rubbish. Yeah. He's not drinking it. Yeah. For sure, that's rubbish. Okay.